In this video I will present the final version of NeuroCellSim. It has been included a graphical interface in the form of a menu to be able to choose the parameters of the wall and the cells, along with some more recent additions. Future possibilities and future plans will also be discussed. First of all, a menu has been implemented from which you can start a new simulation, load a saved simulation, change the language between English or Spanish, or read some general information about NeuroCellSim. When starting a new simulation, certain characteristics of the wall, cells, and neural networks can be modified. In the information panel of the simulator, buttons have been incorporated to restart the simulation with the same parameters. Choose the characteristics of a new simulation, load, save, and basic information about the use of the simulator. Among the most relevant development is the possibility that cells can be mortal and die due to age, as well as by starvation. At this point, it might be appropriate to make an assessment on the performance of neural networks during the development of NeuroCellSim and the current version. In early versions, cells seem to adapt more quickly to the environment and achieve higher speeds and higher performance. In the latest versions, although well-performing cells are also rich, it seems to take more time to develop proper neuronal architectures to find food in the longer term. This change in the speed of adaptation, apparently counterintuitive after having implemented a learning process, might be due to the same factors of the spiking neural network paradox, along other considerations. First, it is possible that, as with spiking neural networks, the learning process does not represent any advantage in the short term. Let us remember that the world they can perceive and its demands, especially in times of low population and lots of food, are very simple. Although they should be able to learn, the world is completely random. There is literally nothing to learn. It is also important to note the effect of simulating sexual versus asexual reproduction. Asexual reproduction placed greater demands on the reproductive cell since it didn't depend on any other cell and needed to store more energy to reproduce. On the other hand, with sexual reproduction as configured in NeuroCellSim, it requires less energy from each parent, and even in some cases, it is enough to be in the right place at the right time, as in real life. Therefore, it is to be expected that some cells that would not reproduce if they were asexual can do so. Because of this, some cells can inherit useless and even disruptive connections. In NeuroCellSim, a multitude of parameters can be modified over different ranges and magnitudes. Relatively few settings have been explored in the last videos. In fact, most of the parameters have not changed. It is possible that, among all the possible parameter settings, there are other niches where cells can thrive just as well or even better. At this point of the development, therefore, it would be unproductive to continue improving neural networks or their learning. Instead, it would be more beneficial if the environment were more complex. To make use of the learning process, it would be necessary to provide the neural networks with something to learn from their environment. Not only does the simplicity of the environment limit the potential of neural networks, but the mere existence of the edges of the simulator, with in addition they cannot perceive, also limits on many occasions the successful maneuvers they can perform to get closer to the food and often traps them. One way to avoid this would be to create a world without borders, unlimited although finite. In this sense, in fact, it would be more like the natural planetary environment. From a topological point of view, this involves certain representation problems, since it is mathematically impossible to represent the surface of a sphere on a flat screen without deforming it. There are, however, two feasible ways to achieve a similar effect. The most direct is to create a sphere and have the cells move across its surface. The user could move above the surface of the planet and observe from there. Another alternative would be to keep the 2D perspective of this version of NeuroCellSim, with the difference that the opposite ends of the simulator would be connected. In this way, the surface will also be finite but unlimited. In this case, it must be noted that the surface represented in the simulator will be not that of a sphere or a planet, but that of a torus. Although NeuroCellSim development ends here, this simulator serves as a mount from which to observe future possibilities. Not only could a more complex world be created around neural networks and more similar to a planet and its natural cycles. These inputs, more similar to the natural ones, should generate outputs, behaviors, more similar to the natural ones, at least in some aspects. For example, seasonal cycles of abundance and scarcity of food or vegetation would cause cyclical migratory movements. In addition to enriching the environment, other promising possibilities include the following. A more complex world would open up the possibility of providing neural networks with more or different inputs to make them more sensitive to their environment or increase the definition and quality of their senses. It is possible that if the neural network had different types of inputs, different senses, it would develop modules of relatively independent neurons and neural structures to process information in parallel ways. As previously mentioned, the cells in NeuroCellSim receive all information regarding the distance to the nearest food. However, if they could also see each other or perceive the colors of other cells, some of the consequences that it could have would be that competition increases when it comes to getting food, and speed and precision prevails even more. The perception of color and the behavior of other cells over time could in turn modify that of others. In a more variable environment, it might be desirable to have a larger number of hidden neurons. Indeed, biological brains have several orders of magnitude more hidden neurons. However, the greatest potential of having more neurons is that the number of possible connections increases exponentially as a function of the number of hidden neurons. This allows the number of possible synaptic configuration or neural architectures to explode from a certain number of neurons. Around 1,400 hidden neurons have the potential to contain 1,000,000 possible connections. So therefore, with the right number of hidden neurons and the right synaptic waves, a neural network could be adapted to any environment. It would also be interesting to stop to examine certain structures that have appeared in some of the neural networks shown in the latest videos, and it is to be expected that they appear more abundantly and in more elaborated ways in larger neural networks. These structures can arise from the network of connections and possibly can exert some kind of function for the neural network. They are, or are made of, synaptic loops between 3 or more hidden neurons. That is, when the connections of a certain number of hidden neurons form a closed circle. These synaptic loops works as an information attractor. Some of the information that comes in goes out, but another part remains and performs another cycle, and so on. As it progresses, the trap information loses its strength and becomes less relevant when new information still comes in. The particularity of synaptic loops is that they can be considered as larger neurons made up of other neurons and some of their connections. The information that enters the loop can be considered as the input of the loop, which it processes with its own neurons and connections and expels as output to the rest of the neural network. Although synaptic loops can be compared to larger neurons made up of neurons and connections, they work in a special way. As the inputs that enters the loop fade as they pass through the connections, what ends up leaving the loop is, in a way, an echo of the loop input that affects the behavior of the cell afterwards. In addition to being able to increase their size, they can also be placed in series, in parallel, as elements of an electrical circuit. Furthermore, all of these loop circuits and combinations can close in on themselves and create even more complex loops made of loops. In bigger neural networks with more connections, loops are easy to form, so the potential of synaptic loops is infinite for large neural networks in terms of their ability to generate nonlinear outputs. From a cybernetic point of view, in elaborated neural networks, these loops and the loops of loops could be hierarchical structures of control one over another. Although the neural electrical potential system still needs to be further improved, it would also be interesting to explore the information that can be extracted from the patterns and frequencies of neural impulses and their variations over time. More outputs and behaviors. Neural networks could be endowed with more outputs dedicated to different actions such as predating other cells, interacting and modifying their environment, communicating with each other. Another alternative would be to equip cells with moving parts to move or perform different actions depending on the particular neural network. In general, the addition of more outputs would lead to a wider range of behaviors and eventually, perhaps, a differentiation between different types of cells if their environment were sufficiently different or it became necessary to explore various evolutionary niches. Language and communication. One of the most promising ways to improve the simulator would be to equip cells with a form of language-based communication. Of all of the forms of communication, language can be useful for two purposes. It could be possible to identify the synaptic loops with basic elements of language, words, ideas, or concepts and the theory restrictions together along with the learning processes as the basis to establish a kind of universal grammar. Once the language is established, some way to translate it for the user could be found. Finally, a very relevant mechanism at the neurological level that is absent in NeuroCellSim is that of neurotransmitters. Neurotransmitters play a fundamental role in exciting or inhibiting neuronal potentials in biological brains. Therefore, in a different environment, it might be useful to include a system or process similar to that of neurotransmitters in their operation. Finally, know that the development of NeuroCellSim has been completed. On my part, I will dedicate the next few years to restart this project in C++ with the idea of remaking NeuroCellSim from scratch in a planetary-like environment with far more possibilities and improving what I have already learned.